Hey everyone, Houston Math Prep here to talk to you about systems of nonlinear equations. If you think back to systems of linear equations where both of the graphs are a line, then the intersection point of those lines represents a solution, right? It satisfies both equations at the same time. So if we have intersecting lines, that's one unique solution at the intersection point. If we have parallel lines, remember we had the case where those lines never intersect, so there's no solution to that system of equations. And then we also might have a situation where both lines lie exactly on top of one another. In other words, the lines coincide, and so every single point on those lines is a solution, giving us infinitely many solutions. The idea of an intersection point being a solution for a system is going to remain the same as we move into nonlinear systems of equations. We may still have a line for one of the equations, one of the graphs may still be a line, but at least one of the equations in the system is not a line when we're talking about nonlinear systems. Generally, when you do this in a precalculus setting, as we're going to talk about in this video, a lot of the graphs that you'll see are parabolas, some sort of quadratic equation. We might have cubic functions or other higher polynomials, and maybe some of the conic sections with circles, ellipses, hyperbolas. Of course, there are many other nonlinear systems, things like graphs of trig functions, exponential functions, logarithmic functions. A lot of those become difficult to solve when coupled with polynomials. So we're going to be exploring the types of graphs that you really see here. Again, keeping in mind that the solutions will occur where the graphs intersect. And in our video here, you can see in order the specific examples that I'll be covering, so you can skip to a specific example if one looks good to you. Our first example, we'll be doing a parabola and a line where they intersect in two places. Next, we'll be doing a circle and a line that do not intersect. Example 3, parabola and a circle with 4 intersection points. Next example, number 4, will be a parabola and a circle with 3 solutions. And then our final example will be a cubic function and a line that intersect in 3 places. Looking at our first system, we have y equals negative 2x squared plus 3x plus 1, which is a parabola, or the graph. And then we have the equation y equals negative x plus 1. This looks like mx plus b form here. The graph of this equation will be a line. So we have a parabola and a line. Now it's possible the line misses the parabola entirely, or just brushes one point on the parabola, or intersects it twice. Now there are two ways that we've solved linear systems. We've solved by elimination and we've solved by substitution. Since you can see both of these equations really have y equals, that means that these expressions of x should be equal to each other since both things are equal to y. So what we're going to do is a substitution here, where I simply take this negative x plus 1, since it's equal to y, and plug it in to the other equation for y. Okay, so that will give us negative x plus 1 is equal to negative 2x squared plus 3x plus 1. Once we've decided substitution or elimination and done one of those successfully, what we'll need to do is then look at what's remaining and decide a proper solution method based on the algebra that we know up to this point. Since I see that this is now a quadratic equation, the highest term involves an x squared and it's a polynomial, we'll go ahead and get everything on one side, set it equal to 0, see if it's possible to solve by factoring. If not, we might have to use quadratic formula, etc. So since my quadratic term is negative, I'll go ahead and move everything over to the left. So I'm going to add 2x squared, subtract 3x, and subtract 1 over to the other side here. And so then that will give us 2x squared minus 4x, we'll have 0 there, is equal to 0. Okay, we can certainly factor this. Greatest common factor will work here. We can go ahead and factor out a common 2x, leaving us with x minus 2. And so now that we are factored, we can go ahead and set these factors equal to 0. So that will tell us 2x equal to 0 will be a solution, and x minus 2 equals 0 will be a solution. Of course, this one here gives us that x equals 0, and this one here will give us that x equals 2. So we are going to start building solutions based on these two x values, okay? So one of them is going to be that x equals 0. So if we go ahead and set up x equals 0, I'm going to go ahead and use the linear equation. We'll take that, we'll put it in here. And so that will give us y is equal to negative 0 would just be 0 plus 1. And so then y would be equal to 1. And if our x is 0 and our y is 1, then that means our intersection point here is 0, 1. So that's one of the solutions. If we look down here, x equals 2, let's go ahead and use that. So if x equals 2, and I plug that information into my linear equation there, I will get y equals negative 2 plus 1. Of course, that will be negative 1. So when x is 2, y is negative 1, and we'll get an intersection point of 2, negative 1. Now with systems of nonlinear equations, what we'd like to do is go back and plug both answers in and make sure that it satisfies both equations. There will be instances where if we solve a particular way and then we plug back in, we might get something that's a false solution, so we do want to go back and check. I'm going to go ahead and move over to the graph here, and you should be able to see that 0, 1, and 2, negative 1 are our solutions for this nonlinear system. We have our parabola that opens down. We have our line, of course, with slope negative 1 and y-intercept positive 1. And you can see 0, 1, and 2, negative 1 satisfy the system here. Moving on to our next example, x squared plus y squared equals 16. This is a circle. It has a radius equal to 4, and its center is at the origin. And here we have a line, right? So this is a line. We want to think about, does the line go through the circle at all? It might miss the circle entirely, right? It might go through just an edge of the circle, one point. It might go through sort of the middle of the circle and hit it twice. We want to find out what we're going to do here. Now, if we look at this system and we think, well, should we use substitution or elimination? What you'll notice is there are no like terms whatsoever in this system the way it appears given to us, right? X squared and x are not like terms. They are the same variable, but they're not like terms. So I can't simply add and subtract copies of x squared and x and eliminate one of them. Same thing with y. I have a y squared and a y term. So really this is set up for us to do some sort of substitution. Okay, so what I'll do is I'll go ahead and easily solve this bottom equation for x. So we might get something like x is equal to 10 minus 2y. And then what we can do is take this information for x and use it as a substitution up here in the other equation. So let's go ahead and do that. So that would be 10 minus 2y squared plus y squared equal to 16. Okay, so we'll go ahead and do a little bit of squaring. Now remember, that's that factor times itself. So if it helps you with the algebra to write two copies next to each other so you can distribute, FOIL, all that stuff, and make sure that you get the correct thing, that's fine. So our first term here is going to give us 100. We'll get minus 20y and minus 20 more y, so that's going to give us minus 40y. And then here we'll get plus 4y squared. We'll have another y squared from this term here equal to 16. And then what you might notice, that'll give us 5y squared minus 40y, if I write them in the usual order, plus 100 equal to 16. Since I see that this is a quadratic equation, just like before, we have our highest power being the square term here, the quadratic term. So I'll go ahead and try and solve this, maybe try factoring. It might not factor though, right? These are interesting numbers here. Let me at least move the 16 over if we're going to factor it at all, or use the quadratic formula. We do want everything equal to 0. So 5y squared minus 40y, subtracting 16 is going to give us 84 there. Okay, so we might be able to figure out, factors of, for example, 420 that add up to negative 40. We might not. So let's see if we can use the quadratic formula, right? So if you remember, now you might remember the quadratic formula, but I'll write it out here. So in this case, it would be y equals, right, negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case here, we would have y equals negative b would actually be a positive 40 here, plus minus b squared, we get big numbers here. That's okay. 1600 minus 4 times 5 times 84. All over 2a, which is going to be 10. Now, the thing that's interesting here, I think, if we do this thing under the root, 1600 minus 4 times 5 would be 20. 20 times 84. This is actually 1600 minus 1680. So what we're going to get under the root is we're going to get a negative 80. And if we get a negative number, of course, what we're going to end up with are complex numbers, right? Non-real numbers for our solution. So when that happens, the only thing that works for y would be a non-real number, okay? And in that case, we're going to actually have no solution for this system. If we look at the graph of the circle and the line that we have in this system, what we'll notice is that the line goes just over the circle, just a little bit, right? It is close to touching it, but it does not exactly go through any point on the circle. No intersection points means no solution for the system. Let's look at another one with a circle here. So this one is a circle. X squared plus y squared equals 9. So if you think of this x squared plus y squared equals r squared, then the radius is 3. This is centered at the origin again. And this other one here is not a line this time, right? Y equals x squared minus 9. So this is a parabola. This parabola opens up. It has an intercept of -9 on the axis, right? Okay, so we have a circle and a parabola. So it's possible that they don't hit each other at all. You could imagine a situation where you have a circle and a parabola opens away from it. Or maybe it goes through it a couple of times. We'll have to see what happens here. So in this one, we have some options, I think, right? I do see that I have some like terms, so we could do elimination. We could also do substitution here, right? So what I'll maybe do is I'll go ahead and move the x squared over. And let's see what we have. So if I'm going to write down this first equation one more time, x squared plus y squared equals 9. If I go ahead and move this x squared over to the other side, that would make it a negative x squared plus y equal to -9. Okay, and you may work this out a little bit different and do a substitution, and that's okay. For this one here, though, the way I have it set up now, you'll notice I can add these equations together, and the x terms reduce to 0, so we get y squared. Be careful, you can't add these together. They're not like terms, right? So we just get y squared plus y, separate terms. And then over here, 9 plus -9, we end up getting 0, so that's nice. It's already set up for us to factor. So now if I'm going to solve this for y, of course, I could factor out the common factor of y, and I'd have y left over in the first term and just 1 left over in the second term. And with those factored, of course, then the first factor is already solved for us. We would get y is equal to 0 for that one. And if you set y plus 1 equal to 0, that's going to give you y equals -1. Okay, and what we'll notice, I think, when we plug in things, we don't always get the same x values that go with different y values, right? So let's look at this first one here. So y equal to 0. Let's go ahead and plug that in. I'll plug it into maybe my top equation here. So if I plug that in there, then that's going to give me x squared plus nothing, right, is equal to 9. And if we solve by square root, remember the side that doesn't have the square gets plus or minus, right? So plus or minus, and what's the square root of 9? Of course, that's going to be 3, right? So there are actually 2 x values that go with this y value, right? So this tells us that 3, 0 is a solution, and it also tells us that -3, 0 is a solution, okay? Since you have multiple x values going with this same y value, what you might also see as an answer, you might say plus or minus 3 goes with 0 value of y, right? So we might write those together. This y equals -1. Let's go ahead and do that. So y equals -1. If I plug that in, let's say to my circle equation here, then I'd get x squared plus -1 squared would be a +1, right? Equals 9. Subtract that 1 over to the other side, so we'll get x squared is 8. And then when we square root both sides, of course, don't forget that the other side again gets plus or minus. So plus or minus √8, which is not a perfect square like 3 was for 9, but we can reduce this, right? So let's go ahead and say that x is equal to plus or minus. We're going to pull out the square root of 4, which is 2. That would leave a 2 still on the inside, right? So plus or minus 2 root 2. And both of those x values are going to go with the y value negative 1, right? So we have a couple of things. We have 2 root 2 comma negative 1. We also have negative 2 root 2 going with negative 1. We could write this one as a pair also. You might also see this written as plus or minus 2 root 2. Both of those x values going with negative 1 as a y value. But you can see we should get 2 here, and we also get 2 here as well, right? Written as a pair here and a pair here. So we have 4 intersection points. So we have 4 intersection points. If I show the graph of this system, here we can see those. We've got some decimal interpretation here. But we've got the parabola basically going through 2 points on the left side and on the right side of this circle here. Let's look at another one here. Here we've got a circle and a parabola, but we're doing something different here. So we've got a circle here. Its radius is 2. It's centered at the origin. This is a parabola here. Now this is an x equals y squared parabola, so it's not actually opening up or down. It's actually opening to the right because x is our linear term here. So if we go ahead and think about how would we solve this, you already have x equals, so you could certainly take this and plug it in for x and square that. I'm going to do something slightly different like I did on the last one. I'm going to move the y squared over. I'm going to do this by elimination. So if I go ahead and copy down the first equation again, and then if I subtract the y squared to the other side, x minus y squared is equal to negative 2. Now, if I add these together, of course, the plus y squared minus y squared will add to 0. Here, these are not like terms, so just keep them separate. X squared plus x is what's left on the left side. Of course, 4 plus negative 2 is going to give us 2. And now just, from my elimination, I get a quadratic equation. So I'm going to go ahead and get everything on the same side. So I'll subtract the 2 to the other side. So I get x squared plus x minus 2. This is actually factorable. If you stare at it for a minute, you might see it's x plus 2 and x minus 1 equal to 0. So if you set each of these factors equal to 0, if you set x plus 2 equal to 0, that's going to give us negative 2 for one of the x values. That might work. And then x minus 1 equals 0, that will give us x equals 1 as something that might work. And so let's check out both of those. So if we look at x equal to 1, maybe I'll go ahead and put that into my parabola. So here 1 is equal to y squared minus 2. If I add the 2 over to the other side, then that will give me 3 is equal to y squared. And then square rooting both sides, the side that doesn't have the square gets plus minus. So this is actually plus minus root 3, right? So think about what we've got here. This is 2 possible y values with 1 x value. So this would give us 1 comma positive root 3 and 1 comma negative root 3. Okay, we might also write that as 1 comma plus or minus root 3. Okay, so that is 2 solutions right there. Let's look at when x is negative 2. So I'll go ahead and take my negative 2 and put it in that equation there. So x equal to negative 2. We'll go ahead and get negative 2 is equal to y squared minus 2. Of course, adding the 2 over to the other side gives us 0, right? And then the square root of 0, of course, is going to be still 0. So we only get one y value that goes with this x value, right? So when we have negative 2, we just get 0 only. So we have 2 solutions here with an x value of 1. We have 1 solution here with an x value of negative 2. And if we go ahead and go to our graph of this nonlinear system, you will see that we do get 3 solutions. We get sort of this symmetry above and below the axis, right? So here's 1 plus or minus root 3. But then it touches just the very left point of the circle, the parabola does, and so we do just get the 1 point there. Okay, 3 solutions for that system. Let's go ahead and look at one final example here. We've got a cubic function, right? And then here we've got y equals mx plus b, it looks like. So this is a line. So we have a cubic function and a line for this one. Now what I'm going to do, because they're both set up as y equals, I think that's nice for substitution. You could do some sort of maybe eliminate some things, but let's go ahead and just take this x minus 2 and plug it in for y in the other equation there. Right, so if we do that, that'll give us x minus 2 is equal to x cubed minus 4x. Okay? Now, this is where we get to something that's a little bit interesting. You go, well, we have a cubic function. How do we solve cubic functions? You might not have done a lot of solving with cubic functions. They're a bit more complicated to solve than quadratics, right? But we can at least get everything on one side equal to 0. So I'm going to go ahead and bring everything over to the right side where my x cubed is already positive. I'll subtract x and I'll add 2 and at least get everything equal to 0 and see what we can do with this. Okay, so we'll get 0 is equal to x cubed minus 5x plus 2. Okay, and so what you want to start doing once you get out of sort of linear land and quadratic land, you want to start thinking about what are some solution methods that you might have learned already to solve these. And one of the things that you might want to do to try and factor this to see if there are any what we call rational roots and use the rational roots theorem, we might then resort to something to find possible factors, something like synthetic division. Right? And think about, what numbers can we try that might be zeros, might be solutions for this, right? Since I've already worked this problem out before I made it one of the examples in the video, I do know that 2 is a 0. So what I'm going to do is I'm going to go ahead and set this up for synthetic division. And if you don't remember synthetic division, you may want to go back and review that. Or if you feel like this is beyond the scope of what you're going to be asked to do, then maybe, the rest of the example isn't for you. But if I go ahead and take this and what it would be equal to 0, that's 1x cubed. Don't forget there's a 0x squared in here that's implied. We have negative 5x. And then we have 2 as our constant. Okay, and if I'm doing synthetic division, I know that 2 is a 0, so I'm going to go ahead and use 2 here. And you'll notice 1 times 2 and add, and 2 times 2 and add, and negative 1 times 2 and add, and I get a remainder of 0 there. So what we might notice, this means x minus 2 is a factor. What's left over would then be represented by 1x squared plus 2x minus 1. And so here I have it factored, and I can start looking at, could I factor this further? The answer is actually no, this doesn't factor further. But I do know from this one, at least, if I set this factor equal to 0, of course, from here as well, that x is 2, that's one solution. Another 2 solutions, maybe, could come from setting x squared plus 2x minus 1 equal to 0. Let's use the quadratic formula here since this doesn't factor. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which is 2 here. And so in this one, what you'll notice is this is actually 4 plus 4 under here. So we get negative 2 plus or minus the square root of 8 all over 2, which is going to be negative 2 plus or minus 2 root 2 over 2. And then this actually is going to give us, if I split this up, I get negative 1 for the first part of the fraction, plus or minus the 2's will reduce here, so we get root 2. And so we actually have, you can see there are 3 x values that work here. We get 2, and then we get negative 1 plus root 2 and negative 1 minus root 2. Okay, so those are our x values that might have y values that go with them. Okay, so we have 3 x values. Of course, what we could then do is plug those back in. I would plug them maybe into my linear equation. That looks much easier than plugging them into the cubic, right? Let's go ahead and do that. We'll plug that into x minus 2. So if I go ahead and take my x equals 2 and plug that in there, of course, that's going to give me 2 minus 2, and that will give me that y equals 0. If I take this one and I plug it into y equals x minus 2, well, then this one would say that y is equal to negative 1 plus root 2 minus 2. Of course, these things can go together. That would mean that y is equal to negative 3 plus root 2. And then a similar thing happens here if I take my negative 1 minus root 2 and I plug it in to my linear equation there. That's going to give me that y is equal to negative 1 minus root 2 minus 2. And then here y is going to equal, if you combine these, also negative 3 minus root 2. Okay? So now what we don't want to do, we want to be careful here, right? 2 and 0 go together. I think that's obvious. So 2 comma 0 is a solution. What we don't want to do, we don't want to go in and say negative 1 plus or minus root 2 or some x possibilities. And it looks like negative 3 plus or minus root 2 are some possibilities for y. If we write it that way, we don't want to do that. Think about what that's saying. That says any combo of these two with any combo of these two will be a solution. And that's not true. These two do not go together, and these two do not go together. If you write it this way, this is telling us there's 4 solutions here. Okay? Plus or minus this with plus or minus this, you can make 4 possibilities with that. So we want to be real careful and not do that. We want to say that negative 1 plus root 2 only goes with negative 3 plus root 2. And we want to say that negative 1 minus root 2 only goes with negative 3 minus root 2 here. So be real careful that we don't accidentally say more solutions than we intend. Okay, if we look at the graph here, you can see it's not super easy to tell what's going on with some of these. 2, 0 is easy, right? But these were a little bit tricky to find, and we needed that synthetic division to do it. What you'll notice, I think, as you get past quadratics, right, circles and parabolas, you get into cubics or maybe some other things. I'm going to show you one other similar example here, not all the way, but just sort of look at the graph. If I take, instead of a line with, say, a cubic function, and I instead replace it with something like a parabola, what you start to notice here is there are 6 intersection points here. There's not symmetry, right? This is not the same x value as down here. They're not exactly above below one another. You'll notice that, like these solutions here where they intersect, the y values are close, but they're not the same. Some of these get really ugly to solve. So hopefully you're not asked to do anything too crazy in your class. Hopefully everything's pretty manageable. You should expect to do some factoring, some quadratic formula, maybe a little bit of synthetic division if you end up with something cubic, but hopefully not anything too crazy. Hopefully our explanation and examples here have helped you out. Good luck with your nonlinear systems, everyone. We'll see you in the next video.